right, let's talk about thermodynamics. And I know, that word might sound like something straight out of a dense physics textbook, but stick with me. This is really the fundamental rulebook for how energy works. It governs everything from the engine in your car to the cells in your body. Let's dive in.
So think about this for a second. Why does a car engine get hot after a drive? Or why do you heat up after a good workout? That's not a coincidence. Those are real-world, everyday examples of thermodynamics in action, and we're going to unpack exactly why that happens.
And that really gets to the heart of it. Thermodynamics is basically the science of how we turn work into heat. And maybe more importantly, how we can grab that heat and turn it back into useful work. It's the magic behind pretty much every machine that powers our world.
So here's our game plan. First, we'll get the basic definitions down. Then we'll tackle the big one, the first law of energy. After that, we'll look at the 4 main ways energy transforms, see how engines put it all to use, and finally, we'll find out why even a so-called perfect engine has its limits.
Okay, so first things first, what is thermodynamics? Before we can really get into the rules of this game, we've got to meet the key players. So let's define the basics that are at the center of any energy transfer. So in the world of thermodynamics, we always talk about a system. That's just a fancy word for whatever we're studying. It could be the gas inside a piston, for example. Everything outside of that, that's the environment. And the whole game is just about how energy moves back and forth between the two.
All right, on to the first law of energy. Now this is, and I'm not exaggerating, one of the most important rules in all of physics. The bottom line is this: you can't just create energy out of thin air, and you can't destroy it. You can only change its form. It's the ultimate conservation law.
And here it is, the famous equation, delta U equals Q minus W. So what does that actually mean? Well, delta U is the change in a system's internal energy. That change is equal to the heat you add to it, that's Q, minus the work the system does on its surroundings, that's W.
You know, here's a really simple way to think about it. Imagine the internal energy is a bank account. If you deposit more heat than you withdraw as work, your balance, your internal energy, goes up. But if your system does more work than the heat you're putting in, you're making withdrawal, and your internal energy goes down. It's just simple accounting.
Okay, so we've got the main rule, the first law. Now let's look at the different ways this rule plays out. There are 4 key processes, 4 different paths that energy can take, and you see them everywhere.
First up, we have an isothermal process. The clue is right there in the name. Iso means same, and thermal means temperature. So in this process, the temperature doesn't change one bit. What that means is any heat you put into the system is instantly converted into work. Q equals W. It's a clean, direct conversion.
Next, we've got an isobaric process, where the pressure stays constant. A great example is boiling water in a pot with a lid that can move. The heat you add has to do 2 things at once. Part of it does work by pushing the lid up, and the rest goes into increasing the water's internal energy, making it hotter.
Then there's the isochoric process. This one's all about constant volume. Picture a gas sealed inside a super strong, rigid box. If the volume literally can't change, then the system can't do any work by expanding.
And what that means is that the work done is 0, period. So every single bit of heat you add goes directly into that internal energy bank account we talked about, which raises the temperature. It's the most straightforward way to heat something up. And finally, we have the adiabatic process. Now this one's pretty special. It happens when a system is perfectly insulated, or when a change happens so incredibly fast that there's no time for heat to move in or out. So in this case, Q is 0, no heat exchange.
This leads to a really cool result. Since you're not adding any heat from the outside, if the system does work, like when a gas expands really fast, it has to pay for that work by taking from its own internal energy. And what happens? The system actually gets colder. This is exactly why a can of compressed air feels ice cold when you spray it.
So now let's put it all together. Let's see how all these different processes combine to create one of the most world-changing inventions ever, the heat engine. This is where the theory gets real.
So what is a heat engine, really? Well, it's just a device that's designed to take heat and convert some of it into useful mechanical work. And the really important part is that it works in a cycle, repeating the same steps over and over and over to create continuous power.
And pretty much every heat engine follows the same basic recipe. Step 1, it sucks up heat from a hot source, like burning gasoline. Step 2, it uses that energy to do work, like pushing a piston. And Step 3, it dumps the leftover waste heat into a cold place, like the air around it. Absorb, work, release. That's the rhythm of the engine. So how do we know if an engine is any good at its job? Well, we measure its thermal efficiency. Basically, it's a ratio. It tells us how much of the heat we put in from the hot source actually gets turned into useful work compared to how much just gets wasted and dumped into the cold sink. The less heat you waste, the better your engine. Simple as that.
This all begs a really interesting question. Could you, theoretically, build a perfect engine, one that's 100% efficient? Well, a French engineer named Carnot thought about this a long time ago. And he dreamed up a perfect, idealized engine just to figure out what the absolute limit of efficiency could be.
And what he came up with is the Carnot cycle. It's this beautiful theoretical loop that uses the 4 processes we just learned. It starts by expanding at a constant hot temperature, absorbing heat. Then it keeps expanding, but with no heat exchange, which makes it cool down. Then it gets compressed at a constant low temperature, releasing waste heat. And finally, it's compressed again with no heat exchange, which heats it right back up to the start. It's a perfect 4-step dance.
And this is where Carnot made a huge breakthrough. He realized the maximum possible efficiency of any engine doesn't have anything to do with the fuel you use or how clever your design is. It only depends on 2 things: the temperature of the hot source and the temperature of the cold sink. That's it. You want more efficiency? You need a bigger temperature difference.
And that brings us to the biggest takeaway of all. To get that 100% efficiency, your cold sink would need to be at absolute zero, a temperature that's physically impossible to reach. So what that means is that some heat must always be thrown away. You can never ever convert all the heat from a source into work. It is an absolute, unbreakable law of the universe.
So I'll leave you with this question. If even a perfect imaginary engine can't cheat this system, what does that tell us about the fundamental rules of energy? It tells us that thermodynamics isn't just about building better engines. It's about the deep, unbreakable laws that govern our entire reality.